Welcome to Lecture 2 using the text Elementary Linear Algebra 7th edition by Ron Larson. Introduction to Systems of Linear Equations. This is Dr. Gilbert Eyabi. The goals. First, to recognize a linear equation in n variables, to find a parametric representation of a solution set, to determine whether a system of linear equations is consistent or inconsistent, and to use back substitution and Gaussian elimination to solve a system of linear equations. Definition. A linear equation in n variables, the variables being x1, x2 up to xn, has the form a1 x1 plus a2 x2 plus an xn equals b. Now I want you to look at this equation very carefully. If we are asked to solve this equation, basically we would be looking for values to substitute for x1 right up to xn such that the equation is satisfied. We would come back to that later. Now the numbers a1, a2 up to an are coefficients and they are real numbers, and the constant term b is also a real number. a1 is known as the leading coefficient and x1 is the leading variable, which makes a1 x1 the leading term. A quick remark: linear equations have no products or roots of variable, and no variables are involved in trigonometric, exponential, or logarithmic functions. They only appear to the first order. Looking at these two equations below, the first equation, though it may look complex, is a linear equation. X is in the first order and y is also in the first order. The second equation is not that complex, just looking at it, but we see that x is involved in a trigonometric function, so the second is not a linear equation. Let's talk a little bit about solutions and solution sets. A solution of a linear equation in n variables, and n could be relatively large, as we saw before, is simply a sequence of n real numbers s1 to s, such that when substituted in the equation in the place of x1 up to xn, the equation is satisfied. We're going to solve two examples to illustrate the case with parametric representation of a solution set. But before we get there, let's just move on with the introduction of what is known as systems of linear equations. A system of m linear equations, you can count 1, 2, 3 m linear equations, and n variables x1, x2 up to xn, is written in this form. So basically what it has is it has m equations and n variables. We call that an m by n system. Now, a solution of a system of linear equations is a sequence of numbers s1 to sn such that each of the linear equations is satisfied. So how do we find x1, x2 up to xn such that when substituted in each of these linear equations, everything is satisfied? That's a big challenge, and I would be introducing several techniques for solving systems of linear equations. When you solve a system of linear equations, you have one of the following results. Number one, there may be no solution, in which case we say the system is inconsistent, or we may have exactly one solution, or also known as a unique solution, in which case we say the system is consistent. or we may have infinitely many solutions, in which case the system is also consistent. So we would be dealing with some of these. Now, before we go on with the example mentioned earlier, let's state to you three operations that will produce an equivalent system. And this is very important because we would use these operations again and again to transform systems into what I would later call row echelon systems, or reduced row echelon form, or just Gaussian elimination. The first would be to interchange two equations. So if I interchange two equations, the system would stay exactly the same. It doesn't change. Number two, multiply an equation by non-zero constant. The emphasis here is non-zero. And three, if I add a multiple of an equation to another equation, it doesn't change. The system remains exactly the same. These are very important concepts which we would investigate. Now, if technology works here, that'll be fine. Okay, so let's look at this system together. We have x1 plus 2x2. We're solving this system, equals 4. And let me also state another system here. This will be 3x plus 2y minus z equals 3. Okay, we want to solve both systems. Let's start off with this first system. Solving this would give us x1 equals 4 minus 2x2. Okay. So I can go ahead and set my x2 equals some parameter t, and let's emphasize that t has to be a real number. If I do that, then we have that x1 equals 4 minus 2t, and x2 equals t, with our emphasis that t has to be a real number. Okay, so right here, what we just did, this is a parametric representation of our solution set. From here we can get as many particular solutions as we want. If we decide and say, okay, if t is say 1, then we would have x1 equals 2 and x2 would be equal to 1. Okay, so we can have as many solutions as possible. That is just a particular solution. You observe that this system has one equation and two unknowns. We realize that whenever we have a system where there are more variables than there are equations, there is a conjecture, there is something that is common among those kind of systems. For now, I would not disclose what that is, so I'll let you think about it. So we have here infinitely many solutions. Okay, why don't we try this other system? It has 3 variables, 3 unknowns, and just one equation. Still very easy. Solving these, we have let's see if arithmetic is good enough. We should have x equals, let's see, 1 minus 2/3 y plus 1/3 z. Okay, make sure the arithmetic is good enough. Okay, so why don't we now set our y to be equal to t? Again, we emphasize that t has to be a real number, and set our z, and I always write z that way so it doesn't look like 2, and set our z to be s, that's also a real number. Then we have the parametric representation of the solution set, which would be x equals 1 minus 2/3 t plus 1/3 s, and y equals t, and z equals s, with emphasis that t and s must be real numbers. Okay, this also, just like the first case, this is a parametric representation of the solution set, and we can get as many particular solutions as we want. If we set t equals 0, s equals 0, then x will be equal to 1, y will be equal to 0, and z will be equal to 0, and so on and so forth. Okay, now in the next lecture I would introduce you to the idea of Gaussian elimination or row echelon form. But for now, we know the definition of a system of linear equations and the idea of a parametric representation of a solution set. Okay, thank you very much.